How do I share?
Here, also start again.
Oh, it is shared. Oh, okay. All right. Do I need to put on this one, or is it not needed? Is it needed? Oh, thank you.
So one small thing. Yeah. We have not talked about photodifractives.
But I'm going to do that now.
Do them. So what should I start?
So I was
Mentioned that photographic interferometry, but then we jump into that.
it's a lot, right?
Yeah. Should I start with the basics of photography?
I have the basic photography now. Yeah. So I was kind of thinking maybe after this one, after
This
this,
is yesterday's.
yeah, but I have not finished.
Yeah.
So I'll talk about this one, and then I was kind of in propagation. And this transfer function for propagation is important because we need that in order to propagate, any kind of optical field over some distance of propagation. And more than likely, you'll be using this paraxial transfer function for propagation. The paraxial transfer function is here, and the reason it's paraxial is because it's a solution of the paraxial wave equation. The paraxial wave equation is derived, as you remember, from the Helmholtz equation. The Helmholtz equation was here. So if you start from the Helmholtz equation, you can get the non-paraxial transfer function for propagation. Yes, it is more exact. Sometimes people use that, but in most cases, you can get by using the paraxial transfer function. Are you okay so far with that? So the paraxial transfer function is of this form over here. So if you have, a black box, as it is called. So this is something that people in engineering, electrical engineering often talked about. If you have a linear system, it can be represented as a black box. My box is not black, it's white, but okay, it's said to be a black box. So if you have a certain input, you get a certain output. The relationship between input and output can be written either, in this case, in the space domain as a convolution, or in the spatial frequency domain as a product. If it's in the space domain, the convolution is between the input and what's called the impulse response of the system. And the impulse response of the system, the small h, is really this part over here. And the reason this is the impulse response of this linear system for propagation is because you see this really is the coaxial equation for a diverging spherical wave. Okay, why? You have a point source. Okay, point source is like an impulse. So what comes out from the point source is a diverging spherical wave. And diverging spherical wave can be written in terms of, this kind of a complex exponential. Why? Because if you take this, you multiply it with e to the minus j k0, and forgive me if I say z because I've been in America for too long, but z, okay? So e to the minus jk0z, if you multiply them together, then you can show that that's just like e to the minus jkr, okay, divided by, of course, r. The r is, what z stands for here, or z stands for here. So that's the expression, as you know, for a diverging spherical wave. A diverging spherical wave can be written as e to the minus jkr divided by r, right? So this is the impulse response for propagation, and this is corresponding to the transfer function for propagation. I prefer to work with the transfer function just because it's much quicker. Taking a FFT and then multiplying by this transfer function and taking inverse FFT is a much quicker process than doing this convolution integral. But remember that convolution integral, we'll have to deal with it a little bit, so I'll come back to that a little bit later on. We also yesterday said, okay, if you did start from the Helmholtz equation, you can get the so-called non-paraxial transfer function, which is here. Non-paraxial transfer function reduces to the paraxial transfer function if you just take a binomial expansion of this. That means if kx, ky is much less than k0, which means that the angles at which the planes waves are propagating is small. That's really what it means. And if you take the non-paraxial transfer function, its inverse transform is, the same as, like the expression for a diverging spherical wave. And we talked about the relevance of the angular plane wave spectrum. You can take any arbitrary optical field, you can decompose it into plane waves that are propagating at different angles. That's one way to do it. That's mostly what is done here. Or in some cases, you can take the arbitrary field and take it as a superposition of point sources and then propagate each of the point sources. That's called this point cloud method. But that's a fancy name. These days people always like fancy names. Okay, point cloud sounds good, right? I mean, old days, people would just call it, the Huygens principle. Huygens, discovered that, you have wavelets that are coming out from secondary point sources. But that is old-fashioned. Okay, no Huygens principle. You call it point cloud these days. Okay, just to be hip. All right. As I said, back to linear systems. This is what we have understood from the linear system. The linear system we were considering so far, right, was a linear system that modeled just propagation from one plane to another plane. But optics, the part that we will be talking about, is also linear, even if you have just linear propagation, or you may have an optical system. Okay, an optical system may comprise, say, for instance, a lens, okay, or a collection of lenses. So you could have a single lens system, or you can have, say, a double lens, multi-lens system. We'll just restrict ourselves to single lens or double lens. Okay, single lens system is a system where you have, just one lens, you have an object with object distance, and you have image distance, right? So if you consider that to be a system, okay, then you can just consider going from the object plane of the imaging system directly to the image plane of that imaging system. That's also a linear system. But that linear system is comprised of first some propagation to the lens, then multiplying by the lens function, as it is called, or lens transparency function, which is a quadratic phase function, and then further propagation to the image plane. But if you take that whole system together, you can represent that as a linear system. Once again, the linear system will be characterized by an impulse response or equivalently a transfer function. That impulse response, okay, typically has been called the point spread function. That's another name for the impulse response because it's a no-brainer. It means how much a point spreads. So if you have a single lens system, okay, if you have a single lens system, ideally, a point should image to a point, right? If you had everything perfect, if the lens actually, more importantly, was a ideal lens, meaning a thin lens, no aberrations, and the aperture of the lens was infinite. But you cannot find lenses like that, right? All lenses will have, say, some aperture, okay? That aperture is called the pupil function, okay? If you have a lens with a certain pupil function, okay, then you can define the so-called impulse response, or as it is called, point spread function of that linear imaging system in terms of the pupil function. And that pupil function comes in here. See, this capital P sub f, okay, is really the Fourier transform of the pupil function. So the pupil function is, I have not written it in detail here just because it was kind of a side thing. Small p sub f is like the pupil function. So if a lens has a circular pupil function, the small p sub f is like a circle function, okay? And the Fourier transform of that circle function is what is capital P sub f. So what is the Fourier transform of a circle? Remember we had, talked about the circle business a little while ago. When we talked about these functions, these rectangle functions, so on and so forth, there you could have a circle function as well. Now, the rectangle function has a Fourier transform, and many of you said it's a sinc function, right? If you had a circle function, does anyone know what the Fourier transform circle function is? Yes, please. So circle function would be something like a circ, of course, and then, it'll be circ of R because it's radially symmetric. So it's like like a cylinder, okay, with maximum amplitude, say 1. You take the Fourier transform of that. Does anyone know what the Fourier transform is? Offhand? No? I'm sorry? Not Mexican hat, but close. It's a Bessel function. Right, a J0. Okay, it's a Bessel function. All right. Interesting. You said, did you say Mexican hat? Okay, all right. That's interesting. Do you have a Mexican hat? Okay, so the Mexican hat, no, good point. The reason I say that is because there is the term Mexican hat, yes. So Mexican hat looks like, kind of like a triangle, and it goes down uniformly to the sides, okay? Guess who wrote this Mexican hat first? There's a guy called Tom Cathay. He was at Arizona, okay? So Arizona is close to where? Mexico, right? So you can see plenty of Mexican hats there. But that Mexican hat function really comes from really the autocorrelation of two circle functions. That's where it comes from. But this Fourier transform of the circle function is a Bessel function. Okay. All right. So let's get back. Is this thing changing? Okay. Because yesterday I thought it was not. All right. So this PF, this capital PF is like a Bessel function. Okay, so you take the Fourier transform. Okay, you take the Fourier transform. Now, Fourier transform is a function of spatial frequency, kx and ky. But you don't stop there. After you do that, then you have to replace those spatial frequency variables, kx and ky, by these two variables, which are functions, as you see, of x and y. Because this h of x and y, see, left-hand side is x and y. Right-hand side also better be a function of x and y. So after you take the Fourier transform, then you replace, as it is called, the spatial frequency variables by k0, which is propagation constant, x over di, and k0y over di. And as you see, this guy now is a function of x and y. So this impulse response for a single lens imaging system looks like a Bessel function, zeroth order Bessel function. All right. So that's why, starting from a point, the point is no longer imaged to a point, it has spread because it looks like the Bessel function, the optical field. Intensity, of course, is the square of the Bessel function. Okay. But if you took the Fourier transform of this, okay, which is the capital H, okay, that's called the coherent transfer function of this imaging system, that's simply just going to be a circle function in kx and ky. What it means is that only a certain range of spatial frequencies will go through the lens. That's really what it means. So if you have a point, okay, if you have a point, remember a point, what's the Fourier transform of a point or a delta function? It's 1, right? So what the 1 means is that a whole bunch of plane waves are coming out from the point source at different angles, and each one of them have the same amplitude, which is 1. Okay, so there's a whole bunch of plane waves coming out, a bundle of plane waves coming out from the point source. Okay, that's the plane wave decomposition of the point source. Some of the plane waves will make it through the lens, depending on the angle at which they're coming out. Some will not. Those that are not coming out will be rejected, of course, by the lens. So therefore, they cannot be imaged. So the only ones that will be imaged are those plane waves that are passing through the lens, and they will all reconstitute and form not the point anymore, but this Bessel function. Okay, so that's really the physical reasoning for why you have a spreading of the point source during imaging. But that's a linear system. A two-lens system is also an imaging system, but in this case, more complicated, of course. But in the two-lens imaging system, you neglect, okay, but just for simplicity, you neglect the aperture size of the lenses. You assume the aperture size of the lenses is very big, so that all the plane waves coming out from the object are going through the lens. But in the two-lens imaging system, you prefer sometimes to put what is called a spatial filter on the common focal plane. Now, before that, let me point out, when we talk about, say, a double lens system, I'm talking about a confocal double lens system. Confocal means, the focal planes of the first lens and the second lens are in the same location, right? So if you have an object at the front focal plane of the lens, simple ray algebra will tell you that there'll be an imaging at the back focal plane of the second lens. But if you put a spatial filter, just like the pupil function for the single lens, if you put a spatial filter on the common focal plane, then the output will be different, all right? And again, you can define the so-called impulse response of that two-lens system by, as you can see, the scaled Fourier transform of the spatial filter. So why scaled? Because you see, the capital S stands for the Fourier domain of the small s. So you could put like a small aperture on the common focal plane. So that's your spatial filter. And if you take the Fourier transform of that, that will become what? Like the Bessel function once again. And with scale coordinates, it'll describe the impulse response of the system. So once again, what have you done there? Well, you have restricted the passage of different spatial frequencies. Right? So if you started out with a point, okay, at the object plane, so after the lens, what's going to happen? Well, the point is going to become a plane wave, essentially, right? Because it's a collimated beam. So that plane wave now is falling on that aperture, as an example, on the common focal plane. So then it's just like the problem of having a plane wave illumination of an aperture, and plane wave illumination of aperture in the far field, in a Fraunhofer diffraction pattern, you might know it's Fourier transform, which is like a Bessel function. And what the second lens really is doing is bringing that Fourier transform from the far field to the back focal plane. So that's why in the back focal plane, again, you see the Bessel function. But you can do other fancy stuff. You can put in any other kind of spatial filter. Typically, it's used to do what's called spatial filtering. Okay, so sometimes you could put some kind of function of x and y to get, say, low-pass filtering, high-pass filtering, so on and so forth. All right, so that's also a linear system. Now, the reason why I bring all of this up is because, okay, yeah, at the common focal point. then it will not do the exact, transformation like this. You'll also add on to that the effect of some phase curvature. So that becomes a little more complicated. Right. That's correct. Yeah. Right. So it becomes a little more complicated. But otherwise, okay, it's exactly the same. Actually, if you look at Goodman's book, he does a problem of what happens if you have a slightly misfocused system, but a single lens. Goodman typically has only single lens because old time. Uh, but effect is kind of similar. So the so-called impulse response for a slightly misfocused system is a little bit different. Okay, I'm not going to talk about incoherent systems here because we don't need it right now. But the reason I brought this up, this business of imaging, right? The business of imaging you can do by lens, as typically people do. But guess what? You can also do, and sometimes better, by holography. Okay, holography is also a way of doing imaging. Because why? Just look at it from the broader point of view. You have an object, okay, then you make a hologram. Then you reconstruct the hologram, what do you get? You get really the image of the object. So if no one told you what's happened in between, it's an imaging system, right? Make sense? It's a more complicated imaging system, but it's unique because you know why? If you're just doing like a single lens imaging system, you have put one lens there with a single focal length. But you'll see in holography, okay, every point that you make the hologram of makes its own lens. Okay, makes its own lens. Why? And we'll show the example. If I have a point, okay, say on axis, a point, if I interfere the point with a plane wave, the interference pattern, maybe, do you know what the interference pattern will look like if you have interference between a point and a plane wave? Zone plate, exactly. There you go. So zone plate has, as Professor Singh was saying yesterday, right? The zone plate is like a grating, right? It's like a grating. So that has an equivalent focal length, right? Because it's a function like a cosine of x squared, something like that. So cosine of x squared can be written as e to the j x squared, e to the minus jx squared. E to the jx squared will correspond to a positive, length, e to the minus jx squared to a negative length. So that each one of them have two focal lengths. So every point, okay, makes its own lens or zone plate. And then when you shine the plane wave, say for reconstruction, you're reconstructing from that zone plate, you're reconstructing the image of that point. Right? Isn't that cool? I mean, so holography is a way to make lenses, okay, but lenses, pertinent to every point on the object. And that's why you also get that exact 3D image. All right. Let me talk about construction and reconstruction of simple holograms. Now before that, one thing I'll show it in just a second. So I just said, okay, all of this stuff, right? This holography. If no one said what's going on in between, is like a imaging system, like a 3D imaging system. Now something interesting. Um, Sometime around 1980s, 1982, 83, there was a paper that came out in a journal. It's called the American Journal of Physics. It's a journal that's mainly for physics instructors. Okay, it's a very good journal, actually. So I looked at that, and then I just happened to look at that. So his name is Abramson. Uh, he came up with what is called a ray theory of holograms. Why ray theory of holograms? Well, because, a hologram, after all, as you can see, is like an imaging system. So, if you had a lens, right, and a lens is imaging, you can describe very simple ray diagrams to show how the image forms, right? You can do the same thing for a hologram as well. You can write down the so-called ray theory for holograms. And if you're only interested in locating where the image is going to be, where the 3D image is going to be, the ray theory is enough. Okay, and it's a very elegant theory, and I'll talk a little bit about that because you should keep that in mind. Take the easiest way possible to figure out what's happening during the readout of the hologram. Okay, nonetheless, so the holograms, or sometimes people also call it complex spatial filters, are recorded interference intensity patterns between object and reference. And of course, as you know, you can only record something real, like intensity. Absolute phase cannot be recorded. Therefore, only thing you can record is phase difference. That's why the concept of reference comes in. What you're recording really is the relative phase difference between the reference and the light or the waves that are coming from the object. That's how you're recording the phase. Okay, got it? All right, so there are these different classes of holograms depending upon how you choose to construct them. So like here, this one, these are all cartoons, okay? If you set this kind of stuff up in the lab, just looking at this diagram, it's not going to work. Just because, here, for instance, okay, it's written reference, but then one reference is written in green, one in black, okay? I mean, reference has to start from a laser, and you break up the laser into two parts, and so on and so forth. But the principle is here. So one of them is like the plane wave over here going. The other one is the light that is scattered from the object, right? And someone was asking the question yesterday. Yeah, I mean, you can get a lot of noise also. You can get a whole bunch of noise that are also forming holograms. And when you reconstruct it, you'll see that noisy reconstruction. Okay, but you have to live with it. Okay, so that's what it is. But okay, so the light scattered from the object interferes, okay, interferes with the reference to form an interference pattern, right? And the interference pattern is recorded conventionally on a recording material which used to be a film, right? Now, I don't know if some of you have seen films before. Okay, I mean, I used to go by, as Professor Singh was saying, buy like this little reel of 24 or 36, then you click and shoot some of them out of focus, throw them away, and so on and so forth. But films are still one of the best, and I'll tell you why. Because the resolution in the film is the resolution of the grain size, and the grain size is of dimensions of 10 nanometers. Silver particles have size of 10 nanometers. No CCD camera can ever do that. Max resolution you can get is 1 micron. So, I mean, you have to live with it, but convenience, okay? So you can record, holograms on really cell phone, or, if you want to be more precise, buy a more, expensive detector, but okay. I mean, all those detectors have issues, which is, the typical size is maybe 4 or 5 microns of that order, and there is some dead space also in between, so you have to account for that as well, and so on and so forth. But it works. All right. So this kind of recording is called a Fresnel hologram. Why Fresnel? Because the light that's going from the object is traveling some arbitrary distance, okay, not the far field, some intermediate distance. So the recording is between the interference of the diffraction from the object in the Fresnel region and the reference, which is the plane wave. So that's why it's called a Fresnel hologram. Then you can also have what's called a Fourier hologram. A Fourier hologram is when the light scattered from the object first passes through a lens and then goes to the film. Now, this is not drawn to scale. The distance between approximately the object and the lens is like the focal length, and the distance from the lens to the film should be also like the focal length, because then you're going to get the spatial Fourier transform of the object. Right? So that's why this is called the Fourier plane hologram. And then, of course, you can also do an image hologram.
It's called complex spatial filter.
Because this is one way you can actually, record. You see the Fourier transform of whatever light is scattered from the object. So what is recorded on the film is a pattern which is proportional to the Fourier transform of the object. And if you go back here, if you put that, as your so-called spatial filter, as an example, in a two-lens imaging system, so if you illuminate the spatial filter by light from another object, so then the Fourier transform of the object falls on the spatial filter, which is Fourier transform of another function. And then you multiply those two together, And then in the back focal plane of the second lens, you get the Fourier transform of the product of the Fourier transforms, which is like a correlation or a convolution. And that's typically the function of complex spatial filters, to perform correlation, convolution, image processing. So that's why another name for that is complex spatial filter. And I remember Professor Singh yesterday was talking about the guy called Vanderlucht. So Vanderlucht was a guy, he graduated from, I think, I forgot, Caltech or someplace, and then he was a faculty at Duke, Duke University. That's where he discovered this complex spatial filter, this technique. So it's named after him. It's called the Vanderlucht filter. Some other people after that made what is called the joint transform correlator, which is a slight different variation, but similar principle. Okay, so here, these are the kinds of holograms that can be recorded. We'll be mainly talking about this, the Fresnel hologram. Okay, mainly. All right. Now, one important thing here. So you can only make hologram from the light that is scattered from the object. The part of the light that is scattered from the object depends, as you see, on how the object is illuminated. Okay? So in other words, as seen in this picture, is a very common sense. The most of a hologram you can get will give you, say, the shape of, say, this part of the object, right? Common sense, right? You cannot make a hologram of this part because you're not collecting any light from that part. Does that make sense? So we were faced with this problem one time. So because one of our projects was find the hologram of small particles like a raindrop. Okay, so you shine light on a raindrop. Okay, it's a very complicated thing, and we'll talk about that. It's a practical issue. If you shine light on a raindrop, some light will be reflected, right? But you can only make the hologram from the part of the light that's reflected from, say, one face of the raindrop. So what do you do for the others? Well, so guess what? So what you do is, you have, say, light illuminating the raindrop from different angles, at least maybe 2 or 3 different angles. And then you record all the individual holograms, and then you reconstruct them, and then you do what's called a tomography. Kind of you multiply all those images together, or do something called a radon transform, as they do in a typical CT scan, and then you can get the true 3D shape of that object. Does that make sense? So if you have to really do a hologram of an object from all sides, you need to collect the light from all sides. It's common sense. All right, how do you reconstruct? Well, you have that developed film, okay, and then you shine the reference light back, which is called the reading beam. And if you shine the reading beam, okay, then what you're going to get, as you probably have expected, is 2 images. Sometimes, as it turns out, both the images are virtual. Sometimes, depending on how you're reading it out or how you have constructed it, you can get one virtual image and one real image. All right, so that's the bottom line. So typically, in all the digital holography stuff that we will be talking about, illumination is with a plane wave. The reference during the construction is also a plane wave. During the reconstruction, it's assumed that the reconstruction is using a plane wave as a readout beam. So typically, you would expect a real image and a virtual image. Okay, so how you find it out numerically is either by forward propagation or by backward propagation. So that's how you find out real image and virtual image. We'll talk about that later. So this is the conventional way, okay? And remember another thing, there is this business of angle, okay? This is very important. We'll talk about that. If you put a certain angle between this reference beam that I drew here in green and this object beam, okay? Now, what do I mean by angle? Well, it's an approximate angle. You see, this object is scattering light in all directions, right? Okay, but there is an approximate direction of travel, called that Z or Z. This other guy, okay, is also kind of traveling along the Z or Z direction, but between those two, that average, direction of propagation of this scattered light and the direction of the reference, you can put a little angle. And how much is little? Well, little is kind of in, as I said, typically like 1 to 5 degrees, not more than that, right? And typically, the reason is because if you do too much, then you'll not be able to detect that using the resolution of your detector. But 5 degrees is the max, okay? I mean, in a typical setup. So if you do that, then you have what is called the off-axis hologram. If you have off-axis hologram, then as it happens, this virtual image location goes down, real image location also goes down. What it means is that you can then look at the virtual image, by looking down onto the film, and the real image, of course, you cannot, see. You have to put a piece of paper. Now, one of the comments made yesterday, and that is true, you of course cannot, have the entire 3D image on a plane, right? Because a 3D image will focus at different places. So, you have to move that piece of paper back and forth, and then you're going to find different parts coming into focus, right? Make sense? Now, the digital version of that, again, very simple. The digital version of that, instead of recording on the film, you record on the CCD. In the CCD, typically then you have a matrix of numbers, okay, of intensities. You take that matrix, okay, of intensities, and then use that to numerically calculate the locations of the virtual image and the real image. So we'll talk about that in just a second, how that is done. Uh, Getting back to this business of construction of holograms, as we said, take the simplest hologram. The simplest hologram would be like for a point source, and I've taken this even simpler case, a point source on the axis. Okay, so if I have a point source on the axis, as you know, it gives out spherical waves. That spherical wave is going to interfere with the plane waves to form, as you said, the zone plate. That's my hologram. All right. And so if you want to do that mathematically, okay, so this is the expression for a diverging spherical wave. This is the expression for a plane wave reference, but here I have also included an angle for use later on. So here I've also put an angle, which is like the k0 times sine of theta. So theta is the angle at which these blue wave fronts are going with respect to the axis. So then the intensity pattern that's recorded is the sum of these two and then magnitude squared, right? And in holography, most books they write it in this form. Okay, the reference R plus O. Okay, now what is O? O is not the object. Okay, O really stands for the optical field from the object on the recording plane. All right, so be very careful. I mean, that people are sloppy. Okay, O really means so. If you are finding the intensity pattern, you find the intensity pattern at a certain plane. And that plane is the plane of the recording. At the plane of the recording, the object, whatever is written as O, is not the optical field coming from the object at the source of the object, but it's the propagated field from the object. So that's what O is. So you see, when you take the magnitude squared of that, you have these four terms. These four terms, the first two are called DC terms. Okay, the reason DC is because electrical engineers were analyzing this. And then these other terms are the so-called interference terms, which are of importance. Now, typically the intensity of the object field at the plane of recording should be much less, right, than the intensity of the reference. Otherwise, what's going to happen is this term is going to, kind of become larger, and it's later on going to cause complications. It's also going to, form its own holograms and so on and so forth. So typically, when I do an experiment in the lab, okay, I'll break up the beam 50-50, but then I know that even the 50% of the beam falling on the object, it's not going to be 50% after it reflects off the object, because the object is, some kind of scattering. So typically the amount of light that's going to fall is going to be lower, much lower. So in fact, sometimes I have seen that I need to start with a reference which is much lower than, the object, so that when that second beam falls on the object and then scatters out, its, intensity is already much lower. So you need to just play around with it. Okay, This is the so-called intensity pattern of the interference, which is also the hologram function. So the hologram function has these four terms, and from these four terms, one of them is going to give you, upon reconstruction, the real image, one's going to give you the virtual image. So when you reconstruct it, okay, you see those four terms. One of them, the first two terms are called the DC term. Then one of the other terms, like this guy over here, which is the object times the complex conjugate of the reference, is going to give this. And the last term is going to give you something like this, where you have the complex conjugate of the object. Now, how do you figure out what's going to give you the real image and what's going to give you the virtual image in this calculation? Does anyone have an idea? I mean, I wrote the answer, of course. Can you say why this gives the virtual image? Yeah, can speak up. Yeah. Okay. More than that, actually, it has to do with the phase. Because see, this guy over here, this is the expression for a diverging spherical wave. Right? This is the expression for a diverging spherical wave. So therefore, this has to be the expression for a converging spherical wave. If you go back, or wherever, okay, here, you go back, correct. But I'm using the notation J. Okay, so in my notation, e to the minus j x squared plus y squared, okay, will correspond to a diverging wave. And again, the reason for that comes from, again, the impulse response for propagation. In my case, the impulse response for propagation, remember, was this guy. This impulse response has the minus jk x squared plus y squared. And impulse response means it is a wave, okay, coming out from a point. And a wave coming out from a point will be a diverging wave. So you have to be very careful about these signs. Well, that's another thing. Okay, even if you do MATLAB, whatever, have to be very careful about these signs. Now in MATLAB, you need to write I, by the way. Yes, but the I has the same meaning as J. So you have to kind of keep that in mind. Okay, so here, this is the expression for a diverging wave immediately after the hologram. So if you have a diverging wave immediately after the hologram, what does it mean? That means if I look into the hologram, I will reconstruct the virtual image because here I have a piece of paper. This is my hologram. This is my hologram. From this hologram, some diverging waves are coming out. So that means if I look into it, the source of that diverging wave is some point here, okay, which is the virtual image. You okay with that? And similarly, this guy over here, therefore, will be a converging wave. So converging wave will converge to a point after the hologram. Okay, so that's what is going to give you the real image, or the conjugated image, as it is called. And here, because I have also introduced, you see these guys, the angle. So then it's not only a diverging wave in this first case, not only a diverging wave, but diverging wave traveling in a certain direction. And that direction is, in this case, the minus kind of direction, which is negative with respect to the z-axis. Why? Because I have this exponential plus jk0 sine theta 1. And this one is a wave that is going at a positive angle with respect to the axis. So that's how I get that angular separation, which is needed to resolve the two images. Any questions on that? Audience? Online? So this is the difference, as you know, between the Gabor hologram and the Light-Upatnaik's hologram. So the Gabor hologram did not have the angle. Okay, so therefore you could not separate what's called the twin images. And then Light and Upatnaik's, and of course with the help of the laser, okay, they did a off-axis hologram. The off-axis hologram was able to resolve the two. By the way, a little story, which actually, so talking of stories which Professor Singh was talking about. So, he talked about light, right? He talked about his colleague Gubat Naik. So I'll tell you further a story. So, Light was at University of Michigan, right? When he was doing all this work, this classified work, he did not have his PhD, by the way. He did not have his PhD. So, but he was a very good researcher, right? Now, at the same time, um, I don't know if you've heard the name Francis Yu. He has written a lot of books on optical information processing. He was also a guy. He was also a guy, who worked on information optics. So of course, their areas, intersected because remember, Professor Singh was saying, these guys were all electrical and communication engineers. So Francis Yu was, of course, Chinese, born and brought up in the Philippines. That's where his parents were. And then he moved, like any others, applied and got admission to University of Michigan. So he started working there. So he started working there and he worked, on his PhD from University of Michigan, right? And then, of course, he worked with Leith, but Leith could not be his supervisor because he didn't have a PhD, right? A PhD usually should have a, PhD degree. There are cases otherwise. But okay, so then Francis Yu graduated, and guess where? The first place he found a job was in Detroit, in a university called Wayne State University. Okay, a very dangerous place later on because downtown Detroit is not well known for its safety. Now things have changed. Anyways, so he became a faculty there. Okay, then he moved on to Penn State, where he stayed for the rest of his life, and he was an eminent scholar there. He's now retired. Okay, so now University of Michigan folks wanted to keep, Leith. Okay, so they wanted to make sure he has a PhD, then he could get a faculty position. So what did they do? They came to Francis Yu and said, Professor Yu, can you take Emmett Leith as your student? Yes. So Emmett Leith, of course, had done enough work. So all he needed to do was just write up his thesis. So yes, he wrote up his thesis, and his advisor was Francis Yu. All right. So it's a very interesting story. So now, many years later, remember, Professor Singh was talking about all these awards. There is awards in the OSA, SPIE. One is called the Gabor Award. Another one is called the Emmett Leith Award. It's a very prestigious award. So about maybe 5 years ago or 6 years ago, okay, someone proposed to me to nominate Francis Yu for the Emmett Leith Award, okay, in the OSA. So I said, yeah, of course. So then I, of course, came to know more of this story. So that helped me write actually a very good story about Francis Yu. The first time it was rejected, well, as it happens, okay, fine. But the second time, and notably the time when Optic OSA at that time had its 100th meeting in Rochester, that's where, of course, it started from, he got actually the Emmett Leith Award, which is very fitting. Okay, so sometime, I might have some pictures, I'll show that too. So it's a very memorable moment because the who is the advisor, who is the student is hard to say. But that's the story of Emmett Leith and Francis Yu. And Francis Yu came to be well known for what's called the other kind of correlator, which is called the joint transform correlator. The joint transform correlator original idea was from Goodman, but then Francis Yu really, refined it, and he spent most of his time on that, as well as on, what's called rainbow holograms and so on. All right, so I always find it useful and fascinating to see the connections, how people evolve, because that is instructional in the first place. Are you okay with this? One other little point I wanted to mention, when Gabor made his hologram, as Professor Singh was saying, he just had that little mercury vapor lamp, right? And then he expanded that, made it kind of almost a spatially coherent source and recorded the hologram. And he recorded on-axis hologram. Why? Because that light source, if you now break it up into two parts and then make two different, paths, it doesn't have that much coherence, right? So whatever coherence it has, okay, you just need to pass the light through the object or whatever you have, and then you make the hologram. That's why you have the on-axis hologram or the inline hologram. So another thing I like to point out, so if you have like a, what's called a sparse object, okay, so now this is something I'll bring out here. We might talk about it later. This sparse object is a very tiny object, okay, that's what a sparse object means. The object does not, intersect too much of the beam. So what are sparse objects? Like little particles, bubbles, dust, so on and so forth. So if you pass light through that, like here, okay, if you pass light through a sparse object, okay, there is some light that's going to be diffracted from, the edges of the sparse object, and you'll be making hologram of that, right? And that's typically what is done in inline holography when people do particle field holography. That's what people do. Okay, particle field holography is based on just sending the light in through. Okay, so now the sparse object you can think of as like the absence of an object, right? Remember in optics books, there is this thing called Babinet's principle. The Babinet's principle means if there is an absence of a field, you write it as minus of that field. So instead of writing R plus O, then you would write like R minus O. But in either case, you see, you're recording the hologram of, in this case, the absence of the object or the edges of the object, because that's really where the light's diffracted from. So anytime you see any book on particle field holography, okay, and really a very couple of people did a lot of work on particle field holography. One guy's name is, of course, a good friend of K.R. Singh. His name is Sirohi. Okay. He was actually, again, optics guy. He was the director of IIT Madras for some time. Then he went to other schools and so on. He's retired now. But he worked, another guy, his name is Chandra Vikram, another very well-known guy. He has a book on particle field holography. So these are, again, two well-known, Indians who have worked in this particular area. So keep those names in mind. But I wanted to bring out the fact that you can also, record holograms or sparse objects just by shining light directly. That's good enough. I mean, if someone says you want to know the size of the dust particle or the size of, like the water drop or the approximate outer boundary, then there is no need to go through all this complication. Just send light through, the water drop, and as long as, or the dust particles, as long as, the objects are sparse, you are going to record interference patterns, and the interference patterns of the hologram will really look like small little Newton's rings all over the hologram plane. That reference is, going along, as you can see. That's it. Yeah. The simpler, the better, right? So the hologram that you're going to record is the hologram of the interference between the edge diffraction of the object and the rest of the beam. And finally, what you'll see are a bunch of little, circles or whatever. So in a sense, okay, when someone says what is the like a diffraction pattern from an edge of an object, okay, you do the calculations. That's really also the hologram of the object. Okay, so keep that in mind. Also, that's also important. So it depends on the size of the particle. Smaller the particle, you get bigger rings. In the case of water droplets, when we did these experiments, we just got the diffraction from the edge of the water droplet. So I'll talk a little, since you asked the question. So if you have a water, this took a long time. So if you have a water droplet like this, consider it to be spherical. It's not spherical, it's kind of little conical, whatever, okay, because it's falling through the atmosphere. But let's consider a sphere. So when you send light through this sphere, what's going to happen? First, you're going to get diffraction from the edge. Something else? Anything else can happen to it? Refraction. So light is going to go through it, some part, right? Some part is going to, of course, get reflected, but some part is going to go through, and it will act like a lens, right? A water droplet is like a very small spherical lens. So it was very interesting experiment. We spent a lot of time because I didn't know a thing about it. So, but what's the focal length of the lens? The focal length of the lens is almost like the radius of the water drop, right? You can calculate, using lens formula, you can find out R1, R2, R1 minus R2. That will focus very close, right, to the droplet. So what happens when the light that goes through the lens focuses that close? Well, it's going to diverge at a very large angle. And by the time it reaches your detector, none of that light is there. Okay, so you have no record, really, of the light that's gone through that water drop. So the only information you have is the diffraction of the light from the edge of the object. Okay, so very practical things. I mean, that's why I like this area, holography. I mean, it's down to basic stuff. I can show you some cute pictures of light focusing within the water droplet, actually, when we try to do this stuff. All right. Everyone okay with this? This is some business of reconstruction and so on. But this recording and reconstruction of Fresnel holograms, I mean, we looked at the simple case, but if you have the general case of an arbitrary object, the arbitrary object, has a Fresnel diffraction pattern. The Fresnel diffraction pattern interacts with the object, interacts with the reference, and when it interacts with the reference, you get, the recording of the hologram. Sometimes you can record the Fresnel hologram, sometimes you can record the Fourier hologram, whichever. But if you just consider the Fresnel hologram, then essentially what you're doing is you are reading the hologram formed from the diffraction pattern of an object, which is written here as T of x and y, and the object field at the hologram plane is the psi O. So the interference between this and that is what you're recording, right? Are you okay with this? And then remember, you get the four terms. Okay, so one of the terms, of course, is going to have this psi O. The other one is going to have psi O complex conjugate. So if you start with one of them, say the psi O complex conjugate, if you propagate that, okay, then see this psi O to start with, the psi O complex conjugate, its Fourier transform is capital T conjugate minus kx minus ky times its exponential. Why did I get that? Well, I got that because what is the Fourier transform of psi O? The Fourier transform of psi O is the Fourier transform of capital T, right, multiplied by the transfer function for propagation, right? And the transfer function for propagation is e to the plus j kx squared plus ky squared zo over 2k0. Is everyone with me here? So what's the, what's the Fourier transform of the complex conjugate of psi o? Just by looking at properties of Fourier transform, this is the complex conjugate. Okay? And complex conjugate has picked up the exponential minus. Okay, so now if this one propagates, as you can see, a distance zo after the hologram, then all you need to do is multiply this with the transfer function for propagation, which will have e to the plus j kx squared plus ky squared zo. So these two exponentials are going to cancel out, and what you'll be left is the Fourier transform of your image, in this case the real image. The Fourier transform of the real image is capital T complex conjugate minus kx minus ky. And it's, if you look up the inverse transform, it is, T complex conjugate of x and y. So that's why it is the complex conjugate of the, objects or the conjugate image. And you can do the same thing and figure out where the virtual image is coming from. Okay, here. So as you can see, these calculations are really very straightforward. Again, if you look at Goodman's book, he has gone through the same thing with a lot more calculations, but not much is needed. I mean, it's very straightforward here. Just by going, why? Because I am using the transfer function for propagation. You start using the impulse response, this calculation will go on. No, this follows my book. All the notation here is my notation. The difference between mine and Goodman's, again, if you are comparing with Goodman, number one, whatever I've written as J, Goodman writes as minus J. That's number one. Number two, Goodman usually writes Fx and Fy. I write Kx and Ky. Okay, remember I talked about this ray theory of holograms? Okay, so I just wanted to spend just a moment just to tell you the elegance of this thing. So, if I make a hologram, okay, say I make a very simple hologram. I make a hologram from, this time, not a plane wave as a reference, but a point source as a reference, okay? Now, I can use anything I want as a reference. Okay, so let's suppose I use a point source as a reference. So this R is like the point source. And let's suppose I have an object which is also a point. Okay, so I'm here recording. So this is a good exercise. Okay, and you need to help me along over here. So I am recording, and this is the some of the basics of wave optics, Fourier optics. So I have a point source as an object, point source as a reference. So first, can anyone tell me what the hologram typically would be looking like? What the hologram function would look like? Okay, let's go a few steps back. Okay, no, not hyperbolic. Let me give you a hint. So sometime back I asked, okay, so if I have a point as an object, okay, that previous example, that remember this guy here, this guy, right? I have a point, okay, but now I have a plane wave as a reference, and someone said, okay, you said the interference pattern, which is the hologram, is the zone plate, right? Zone plate, right? Zone plate. Why? Because if you work out the details, it will work out to be like a cosine of some x squared plus y squared. So now look at this one itself. So okay, instead of plane wave, if I had a point source as a reference, then what would be my hologram? What's the difference between a plane wave and a point source? Yeah, point. Okay, yeah. Say that again. So point source gives out spherical waves, right? Plane waves gives out plane wave forms. Okay, but now let's consider this example. So there is light coming from the stars, light coming from the sun. You don't see too much because of the dust here. Okay, but so be it. Let's suppose light is coming from a star. Okay, so when the light comes to you, okay, is it what kind of wave is it? I'm sorry, plane wave. Why is it a plane wave?
It's a small part of a huge sphere.
It's a small part of a huge sphere. Exactly. Excellent. So this plane wave could be also thought of a small part of a huge sphere, meaning that this is also really like a recording of one point with another point, only thing, other point way far away. Right? So if we slowly bring that point closer, okay, I mean, this shape is not going to change too much. It's still going to be a zone plate. How's that?
Symmetric.
Yeah, it will be symmetric. I mean, if the plane wave, if the point source is on the axis, it will be symmetric. Yeah, right. If the point source is up there, it will not be symmetric. But if the point source is on axis, it will be symmetric. Right? How's that? I mean, it's very simple. You don't really need to think, do too much calculations with this. It's just the way you think. And that's what I want to encourage in you. So, okay. So if that's the case, so I get another Fresnel zone plate, right? So if I have a Fresnel zone plate, okay, so then that's my hologram function. Okay, so here the Fresnel zone plate will be centered here, right? It will be centered there. Does it make sense? Because in the previous case, think of that line to be like on axis in a sense. So then the center of the zone plate is going to be here. But now here's something interesting. Can someone again go a little bit further and tell me, so this hologram records the intensity pattern. Intensity pattern has, some bright, dark regions, so on and so forth. Now, zone plate, when you say zone plate, different parts of the zone plate have different periods, right? And different periods, they change, right? If you go further away, the period becomes smaller and smaller. So that means the spatial frequency becomes larger and larger. What would be the so-called instantaneous spatial frequency right there at the center, at the bullseye of the zone plane? Spatial frequency should be zero. Should be zero because why? The instantaneous spatial frequency should be zero because it's continuously decreasing from that. Does that make sense? Here's another reason why. You see, you can decompose this point into a bunch of plane waves. This also as a bunch of plane waves. So in this direction, there are two plane waves, one from this spherical wavefront, one from this spherical wavefront, traveling in the same direction. Now, if two plane waves travel in the same direction, you don't see an interference pattern along the transverse direction. Does that make sense? You only see interference along the direction of propagation, right? So these fundamental concepts are extremely important. So here, this is the basis of this hologram ray tracing theory. So what it says is that in this direction, right there, the spatial frequency of the hologram is zero. That means it's just like a uniform piece of plastic there. Make sense? So then, during reconstruction, if I started out with a reference or reading beam, again a point source at the same point, and illuminated again, this hologram, placing it exactly the same place as the film or recording medium, at that point, that ray, so to speak, is not going to break up, not going to be deviated, not going to be diffracted because the spatial frequency there is zero. So that is what is referred to as the optical center of the hologram, just like you have an optical center for, a lens. That makes sense? Very simple and very elegant. And that's one of the laws of ray tracing through a hologram. Now you can make it more general, okay, fine, but it's a simple case. What happens for a ray that's going in this direction? Well, at that point, when you recorded it, remember you just said it was a zone plate, so there was a certain spatial frequency. So because of the spatial frequency, the light going there will break up into two parts, really three parts, but the important ones are one scattered up, one scattered down, at equal angles, right? So there you have your two laws of ray tracing through a hologram, and you only need two laws to find out the location of the image. And you see, one of the images for this case is going to reappear at the original object location. The other one will be found by the intersection of this line, which is scattered from that spatial frequency, and this line going to the center. So wherever they meet. If the angles are such that they meet on this side, you get a real image. If they don't meet on this side, you get a virtual image. Right? Does that make sense? Okay, are you enjoying this so far? So that's holography. By the way, starting from here, you can also find out these are simple cases. Holographic magnification is also an important thing because when you make a hologram, right? When you make a hologram, your final reconstruction better look like the object, right? If you started from a cube, the reconstruction better look like a cube, which means the horizontal, or I should say the transverse and the longitudinal magnifications better be the same. But that's not often the case, as it turns out, just because of the way holograms are recorded. And okay, if you look at Goodman's book, there is again a long 5-6 page calculation. No need for that. If you go through this little ray theory, okay, you can very easily figure out just by drawing equations of straight lines, find out the intersection, and then once you find the intersection, you can find out the location, the X and the Z location or Z location of the image. And from there, if you take the differential like this, you can find out the magnification. So you're going to find out these other magnifications. And in fact, this also, of course, has to agree with the wave calculations. And these are the same results. Longitudinal magnification is the square of the lateral magnification. And the reason that is so here is because I have considered the recording and the reconstruction wavelengths to be the same. All right. If the wavelengths were different, can anyone tell me what will happen? If I write a hologram with one wavelength and I read out using another wavelength, what's going to happen to this picture? Yeah, these angles are going to change. Why? Because the grating equation. The grating equation has the spacing of the grating. It also has the wavelength of the light that's illuminating the grating. So that's why the angles are going to change. If it changes, you do the same calculations. You'll see here a ratio of lambda 2 over lambda 1. And what that means, and you'll see that also in Goodman's book, is if you record at a certain wavelength, you can reconstruct at certain other wavelengths such that these two magnifications become the same. Right, which is written here. I don't know what the schedule was. It was a time to take a break because I wanted to talk about photorefractive depth of this. Do you know what the say that again? What is the reason behind magnification? Well, first of all, you have to have a magnification because you are wanting to see the object of a certain size. But the reason for the magnification is because if this O, really, this O was not here, but here or here, then the reconstruction locations will be different. No, it is a little bit different, you see, because the lateral size and the longitudinal size are not the same. But you can make these two equal to 1. You make those two equal to 1, yeah, then they're the same. So how do you make that equal to 1? See right here, it's very easy, right? You can make this, this term to be the same as that term. Okay, so how do you do that? By setting this to be equal to 1. Okay. So now what happens if you set this equal to 1? You set this equal to 1, see the ZR, okay? So if you set this equal, the ZRs cancel out, then what do you have? ZO equal to 0. So that's not going to happen, right? So one way you can do it is make the ZR very large. Okay, so if you make ZR very large, okay, see, this is going to go to 1. Replicate the reference beam in the recording geometry, then the magnification comes out. Yeah, there will always be a magnification. There will always be a magnification. The only thing that will happen is magnification may not be the same in the lateral and longitudinal directions. Okay. Yeah, there will always be a magnification because you see here, I mean, these numbers, I mean, you'll come out with a number. So as you see from here, it just depends on what the ZR is or ZR is and what Z0 is. So if you typically the ZR is larger than Z0. Okay, typically. So if you put ZR equals say 3 times Z0 as an example, then you see this number will become something like 3. Right? But then this number is going to become like 9. So then what's going to happen is if you start off with a cube, okay, the cube is going to, kind of look like a box. I'm sorry? We have not actually at all talked about anything with pixel size. Why? Because here I've considered nothing about the recording medium. I have considered the recording is taking place with exactly a replica of all the spatial frequencies. Now, if you had pixels on top of it, that is going to distort the image. Okay. So the main thing that's going to happen is, the point is not going to look like a point. Because, really like if you have a CCD kind of thing, really all that's happening is, you are introducing a little bit of a point spread function to it. Right? Yes. And why point spread function? Because just think of it as a lens, right? Because this is kind of like a lens. You're recording a lens here. But now at the same time, at the lens plane, because of the pixel size and dead space and so on, it's as if you are putting a pupil function there. Okay, the pupil function is a bunch of little squares with the spaces inside and so on. So then when you reconstruct from there, you're going to see the scaled Fourier transform of that pupil function. And the scaled Fourier transform of the pupil function will blur the image. Right? So that's a simple way of looking at it. You are recording a lens, but while you're recording a lens, you're also advertently or inadvertently putting in a pupil function there. And the pupil function is that matrix. Okay, so what was the plan now? Did you know? Are we going to take a break now or? All right, so maybe we should stop. How do I stop the 10 minutes? Okay, so we'll take a break for 10 to 15 minutes. I think the time now is 11:50. We'll meet at 12. Thank you.
I was thinking that you intervened you that there should be some small tea break.
Yeah, yeah, I felt it.
Yeah. It's needed.
No, I was looking at the time. Yeah. So after this, I'll talk a little bit about photorefractive. And then after that,
Photorefractive is such a wide field that it cannot be covered in.
yeah, I'll just cover some basics. Yeah. Just leave it. All right, is everyone here? All right, let's get started. Oh, do I need to put this one? Again, welcome back. I think it's Good afternoon or good early afternoon. So remember we were talking about how to record holograms, and one conventional way of recording is using the photographic film. So I'll just talk a little bit about photographic film, but then we'll talk about photorefractive materials. That's the other kind of, I would say, dynamic recording medium. So I'll talk about that. So these photographic films, as you know, are very basic. They have been around for ages. What photographic films have is really, silver nanoparticles that is deposited on plastic, and really not silver nanoparticles. They're really silver halide, meaning silver chloride or so on. And when light falls on them, they become silver. Okay, very easy to. So when the silver forms, it becomes black, okay, or dark. Okay, so that's the basic idea. And more light falls on it, more darker the region gets. Therefore, if you shine a pattern of light that has bright and dark and bright and dark, those regions that are bright will make, silver more. So if the silver is more, then when you wash out the silver halide, that area is going to have more darkness. And the other area where, no light fell is going to become, more transparent, so to speak. So essentially what you make is a negative of the intensity pattern that falls on the film. Right? As easy as that. And then, two negatives make a positive, as you know. So you take that negative, again, shine light on it, do the same process, and then finally what you have is a negative of a negative, which is a positive. Now, every one of those are characterized by some kind of figure of merit. See, I'm sure many of you have read that in Goodman's book or many other books. Figure of merit really has to do with what's called the intensity transmittance of the light at a certain point going through this, film or, the developed film. So that transparency function is written as tau n. It's kind of the ensemble average of the intensity that's transmitted at a certain point on the, negative, divided by the original intensity I of x and y that fell at that particular point. So as you can see, if the intensity transmitted at that point is lower, then this transmittance is lower, essentially. That's pretty much what it is. So the bottom line is, so this transmittance decreases with what's called increasing exposure. That means more light fell, more silver nanoparticles, therefore darker the region, therefore, the transmittance will become lower for that negative. And there are some standard, terminology that's used. One is called the H. H is the product of this intensity falling times the time of the exposure. And then there is another, I would say, variable in this so-called figure of merit definition that's called the photographic density. Photographic density is inversely proportional to this transmittance. So as the transmittance decreases, photographic density increases. That's the bottom line. And it's typically expressed in a logarithmic scale. So that's, kind of a very short, very quick summary of the whole thing. And main thing, takeaway message from here is, in good quality films, not the ones you buy, like that, 24 roll or 36 roll, but, better quality films always used to come with a little sheet of paper. Okay, that little sheet of paper would have this kind of curve, which is the density versus the exposure curve. Okay, and the density versus exposure curve is what is also called the DH curve. And the DH curve typically has a knee like so, and then has a linear region, and then it has a saturation. Typically, you would like to choose a film that has a larger value of the gradient, because larger value of the gradient, you're going to get more contrast in the picture, and so on and so forth. So this was the standard procedure before. You see, all of these have all these different names. You've heard of these names like Fuji Color, and then Kodak, and Alpha Color, Konica. Those were the kinds of films we would buy, right? And we would develop. Okay, well, those days are gone because now, of course, the CCDs have come in and so on and so forth. But another way of recording is, using these photorefractive materials. So I'll show you another set of slides on photorefractives, but before that, this is just a, introductory slide. Then I'll switch slides. So photorefractive materials. So what are photorefractive materials? The first question. Well, as the word suggests, the photorefractive means, the refractive index of the material is being changed by light. That's what photorefractive means. Is everyone okay with that? Refractive index changes by the amount of light falling on the material. Question is, how does that happen? So this is how it happens. We'll see in more detail pretty soon. So typically, photorefractive materials can be thought of as doped semiconductors, which also have electro-optic properties. Okay, so I said a whole bunch of stuff here. So a photorefractive material is a doped semiconductor that also has electro-optic properties. Okay, so what does that mean? Okay, so silicon. Silicon is semiconductor. You have to dope the silicon to make it work. So what do you do to dope it? You either dope it with N or P. Okay, dopants, right? What's a typical N dopant for silicon? Anyone knows? I'm sorry? Yeah, electron doping, but name a material that could do that actually. Phosphorus, yeah, because phosphorus comes from 2E5 of the periodic table. So one atom is, giving out one extra electron. Similarly, there is p doping, so you can do p doping with like germanium, for instance, right? So using different kinds of dopants, you can get N and P. So let's consider N. So if it's N dope, so what you essentially have done is you have created extra, sources of, electrons, which could be excited. And there are different ways of exciting it, say, to the conduction band. One way is by light, right? So you shine light of the correct wavelength, then some of those electrons from, guess where, those dopant centers, as it is called, will get into the conduction band. And when it gets in the conduction band, they are free to move. And so they can move under the processes of drift and diffusion and so on, right? Those are the typical transport processes for electrons and holes in semiconductors. So same thing in these materials. Okay, so here, when light falls on, say, these kinds of materials, which are typically doped, actually, then that material will release the electrons where light is falling, and then these electrons are going to go to the conduction band, where they're free to move. And, you know, in many cases, you don't need to apply any electric field across this. Then, if you don't apply electric field, the only process of moving is diffusion, right? Because there's diffusion and drift, right? These are the only two. These are the only two ways or mechanisms of moving. The other processes of change of electron concentration is, recombination, generation and recombination. So typically when they move, okay, they will diffuse to some other region where, okay, likely, they will recombine. That's what happens. Recombination happens by them being trapped. The word is called trapped. They are trapped into the ionized states of some of these impurities. Okay, so they are trapped. Okay, so now as a result of that, what you'll see is, so you have kind of now disturbed inside the material the charge distribution, because you took electrons from one place, excited them, then they moved, they got absorbed, like Pac-Man ate them up. So what you have there finally is a non-uniform charge distribution, and non-uniform charge distribution gives rise to an electrostatic space charge field, because Gauss's law in electrostatics that says, the derivative of electric field is proportional to the charge. So therefore, if you have a charge concentration, which is a function of space, you have electrostatic field as a function of space. That electrostatic field, because the material is electro-optic, okay, changes the refractive index. So very complicated process, right? But it works, okay? So I'll show you in the next few slides. I'm going to show you, more detail of that. Are you okay with this kind of basic stuff here? So essentially what you're doing is you are creating, a change of refractive index with the light that's falling on the material. Change of refractive index means you're in general making a phase gradient, right? And in this case, you're making a volume phase gradient. All right, let me move on to the other slides. These other slides are actually courtesy of, some of the slides are courtesy of my friend at, guess where? Air Force research labs, they do a lot of work on these photorefractive materials. And I've been working with them for probably the last 15, 20 years or so on different things. So these slides, many of these slides or the cartoons here are done by a good colleague of mine. His name is Gary Cook. He was originally from University of Southampton in England, which is actually a very good university, and he's in the Air Force Research Labs for the last 20 years or so. Okay, these photorefractives, by the way, some of them are also photovoltaic materials, like lithium niobate. So you can actually use them for generating, photovoltaic current, right? And you can do that. Would you take a lithium niobate cell and put it on top of your home? No, because it's very expensive. So, but they do generate electricity. All right. So this set of slides was really done for another class of photorefractives that were called hybrid photorefractives. Now I'm not going to talk about that. Why was this done? Well, this part was research. Okay. So if you have these so-called photorefractive crystals, but in between you put in actually what is called a sheet of a liquid crystal, as it turns out, then you can actually enhance the performance of these photoreactive materials. Why? Because, typically electro-optic materials, the electro-optic materials, what is the typical change of refractive index? Could anyone say, like, a lithium niobate electro-optic modulator, as an example? Do you know approximately how much voltage changes the refractive index by how much? Has anyone used electro-optic modulator? Okay. You have?
Yes.
Okay. What kind? I'm sorry.
I didn't have it, but I don't remember the parameters.
Okay. Any kind of electro-optic material, you have to apply hundreds of volts, depending on the thickness, of course, because it depends on the electric field. But finally, the change of refractive index is typically a small number, typically like 10 to the minus 4, 10 to the minus 5. That's the typical. So these are stuff, by the way, physics, no physics, doesn't matter. Okay, practical life, try to remember some of these numbers. So why? Because, when you're trying to, kind of talk to a friend, you have to tell him or her, about what you do and so on. So these kinds of small numbers are the things good to remember. I'll tell you a joke. So one of my colleagues, so one time we were asked, okay, you just talk to students. So he said, no, well, where am I going to talk with the students? Well, here in this coffee room. So he said, no, I need an overhead projector or a LCD projector. So I said, no, that's not the way to talk to students. You just stand, in front of a coffee room and just say what you're doing. So that's actually a good thing, because very often these days you also have to work in teams, you have to interact with others, so remember some of these numbers. So anyways, coming back to this, the purpose of this slide was to show that because these inorganic photorefractive materials, their change of refractive index is so low, so what you can do is inside you can put actually a liquid crystal. Liquid crystal, again, I'm talking of numbers. Can anyone say what's the approximate, delta N, which is called birefringence in a liquid crystal? Just approximate number. Say that again. Yeah, but tell me a number. What would be a number? Okay, so those are important. So they are typically like 0 0.1, 0 0.2, something like that. So, but liquid crystal, how much voltage you apply across liquid crystal? Any idea? Hundreds of volts, millions of volts, millivolts. I'm sorry, few volts, right? Like 1 volt, 2 volt, 5 volt. Though otherwise, those liquid crystal watches are not going to work. So few volts. So few volts causes a change of refractive index or birefringence of like 0.1, right? But the thing is, it's kind of slow. Okay, that's another thing. But if you can kind of couple both of them together, you can use the electric field that's generated in the photorefractive material to modulate the birefringence of the liquid crystal, then you can do something better. So that was the purpose of this particular experiment. But we're not going to talk about that just because it's beyond the scope of this short course. Yeah.
It is somewhere like the structure of like modulator.
Please say that again.
The structure is somewhat similar to the specified modulator.
Yeah, correct. That's right. So anyway, so these are some cartoons that he had done to show, how this light changes the, behavior of, say, like the electron. So if you have uniform illumination shining on the material, okay, as you can see, these are electrons that are generated, but then electrons have nowhere to diffuse because the entire region has the same, concentration of light falling on the material, right? But if you went here and then you shine the light, sorry, you here, okay. So if you shine the light only on little part, right, then what's going to happen? Electrons are going to generate there, but then they're going to diffuse to the sites just because, that particular region, had a higher concentration of electrons, so they diffuse to regions of lower concentration. And that's where, of course, they're also going to recombine with the impurities, with the traps. Okay, so this is what happens for non-uniform illumination, but how about this kind of non-uniform illumination? If you had, say, this is just cartoon-wise drawn as two light sources, but they have to be coherent, mutually coherent. So they're mutually coherent light traveling at two angles, you get a sinusoidal pattern, right? So if you have a sinusoidal pattern falling on that, like, regions of bright and dark, so see what's going to happen? That light is going to separate out the electrons into clusters because some regions where the light has fallen, electrons have moved, right? Electrons are generated, first of all, then they move to regions where there is darkness, and then they recombine. So now effectively you have formed, as you can see, a charge distribution, right? So if you have formed the charge distribution, so then these charges have kind of coagulated here pretty much, leaving these regions, devoid of electrons. So they are devoid of electrons means they're net positive charge hanging around there. So you have a charge density, somewhat like that. Okay. This charge density, okay, generates what's called a space charge field through Gauss's law, right? Make sense? Because the Gauss's law, remember what it is? The Gauss's law is the gradient of the the gradient of the electric field equals the charge density. So that means the electric field is the integral of the charge density, right? So if this pattern happens to be like a cosine pattern, so the space charge field will be like a sine pattern, right? Which is an important thing to remember because here what that means is that this space charge field, which of course modulates the refractive index through the electro-optic effect. So that relationship is just a linear relationship. Delta n, if you look up any electro-optics book, delta n equals some minus, some half and n cubed times the value of the electric field. That's the kind of formula. So this is just a linear relationship and in phase. So you see what's happened here? There is, kind of like a phase shift between the intensity distribution and the refractive index distribution. That's typically what happens in many of these photorefractive materials. Not all, many of them. Uh, those in particular where the diffusion effect is the primary reason for the movement of the charge carriers. Everyone okay with this? And there are plenty of materials like that. Barium titanate is a well-known material. Okay. Lithium nowadays, not so much. It has some of this, but it also has something else which is called the photovoltaic effect. All right. So that's a different story. Yes, the polymers are a little bit different story. So polymers, once again, they can be doped with different materials. But in polymers, typically two things different in polymers. Maybe I don't know if I have a slide on that or not. Two things different. Number one, the major source of the charges that are mobile are holes instead of electrons. That's number one. And number two, you have to apply a bias field across the polymer. So in these photorefractive polymers, you need to apply a bias field. Okay, and that bias field, by the way, is not very small. Uh, Typically, you would have to apply, say, if you have a polymer thickness of about, I don't know, I mean, I'm sorry,
2 mm or 3 mm.
much lower. I mean, we have done polymer thicknesses in the order of like 100 microns. Yeah, see, there you go. So those things also, the electric field needed is high, so you have to apply some voltage, some serious voltage, like 100 volts, 1000 volts, for photorefractive effect. For photorefractive effect, yeah. Because in liquid crystals, you apply much lower voltages, like 5 volts. But for photorefractive polymers, for it to work as a photorefractive device, the amount of voltage needed is high. To the point, I mean, the reason I say this, so I'll give you an experience with this. Again, no one taught me this one. So somewhere when I started working with this was kind of in, as I said, late 90s. Then someone said, "Oh, photorefractive polymers are very good." Okay, fine. So, okay, I mean, they are cheap to make and so on. So there was a Japanese professor at Osaka University. So I went there on sabbatical, and he taught me how to make these polymers. Okay, fine. So he's passed on, unfortunately, at a younger age. But anyway, so I learned how to make these, and then in his lab, we were doing two beam coupling experiments. His student was making it, and then I learned, came back. But every time you do the experiments, what would happen is typically you cannot make them perfect. So slowly there would be a little bubble that would develop inside the, just because the polymer has not been sealed very properly. You make them in the lab, so you make the mixture and then you put it between two glass slides and then you apply the voltage. So the coating is not uniform, bottom line. So with use, typically what would happen, a small tiny bubble would develop from non-uniformity. Once bubble develops, if you've been applying that at large voltage, like 500 volts, 1000 volts, that is beyond the breakdown of air. And so then you hear something, a little firecracker, and then that would be the end of that material. So that's my experience. But people had, certainly made it a lot better in fabrication. People at Arizona, for instance, Nasser Pegambarian's group, they regularly make these materials and they last for a long time. And nowadays the voltages, bias voltages are reduced as well. But not down to 10 volts. It is still in the order of hundreds of volts. I'm sorry?
Hundreds of volts per delta.
The delta is actually kind of typically not 0.1, it's probably 10 to the minus 3.
In which we get higher effective for the RNA.
So the liquid crystal you can get, as I said, 10 to the minus 1 delta N. The photorefractive polymer 10 to the minus 5, 10 to the minus 3, minus 2 to minus 3. And these crystals 10 to the minus 4, 10 to the minus 5. In the crystals, in the photorefractive crystals. Yeah. But in the photorefractive crystal, that can be made up by the thickness. Because the thickness, typically you can make them like, in the order of some millimeters, maybe 5 millimeters. So then you have enough change of the phase. Please.
The thickness.
The thickness? No, these crystals typically you would use in the order of millimeters. Right, right. In the order of millimeters. Like the typical crystals would be this size, like 5 millimeters to 1 centimeter. That's the thickness, typically. Yeah, angular selectivity is good. Correct. Yeah. In these photorefractive crystals, angular selectivity can be good. Angular selectivity as well as wavelength selectivity can be good. I'm sorry? Oh, it's much, well, I cannot give you an exact number of the range. I think it's certainly much less than 1 dB. Yeah, much less than 1 dB. So I'll tell you what we are doing currently. So currently we are actually storing volume ratings inside the material, okay? And then we are using it for purpose of image processing. Okay, so I'll talk about that later on. So again, this is a new concept. So exactly as you said, angular selectivity. So we are using the angular selectivity. Why? Because so if I shine an image means some picture into that material. So I take a transparency, and then I shine light on the through the transparency into the material. So that transparency, the optical field from the transparency can be resolved into its angular plane wave spectrum. Right? So those angular plane wave spectrum means it travels, plane waves travel at different angles. Right? Make sense? So if you go into this photorefractive material where you have stored this reflection grating, so what's going to happen? The reflected beam and correspondingly the transmitted beam as well, okay, will undergo, image processing because these different plane waves traveling in different directions are not being efficiently reflected by the reflection rate. Right? Make sense? So very simple thing again. So what we've done is we've taken pictures, typically of the size of the Air Force resolution chart, reduced it down a little bit to the size of maybe millimeter, and then introduced that light into this material, and you can see very good edge enhancement. Okay, from there. Why edge enhancement? Because the light that is not reflected, guess what, is transmitted, right? So the light that is transmitted would be the higher spatial frequencies that are not meeting the Bragg criteria. Make sense? A very simple thing to do. Well, there are difficulties in the experimentation, but see, the physical, procedure is very straightforward. Now, a long time back, I had done work on edge enhancement and image processing using acousto-optic materials, which is also, again, a bulk, but I used acousto-optic grating, in the transmission mode. Okay, you can do the same thing because if you have acousto-optic grating, what it means is that you have, all these planes of refractive index variation created by the ultrasound. And if you came in at a certain angle, like the Bragg angle, then you would get maximum diffraction, right? But if you're slightly off Bragg angle, you'll get less diffraction. As easy as that. That means more light will be transmitted in the undiffracted order. So that's spatial filtering, right? And that's, as you can see, another example. Someone was asking, lensless spatial filtering. You don't need a lens in principle. Okay, you may need a
We are talking about hundreds, thousands of
oh,
nodes.
computer center host. What is the computer center host? You're having some difficulty.
Your video got disconnected again, it's reconnected.
Oh, okay, all right. Okay, so yeah, so lithium niobate is good. Potassium niobate is better. Potassium niobate is faster, actually.
Okay, but if the delta n is of 10 to the power minus 3 or 4, we are reaching that at thousands of volts.
Not in lithium niobate or potassium niobate, you don't have to apply any external bias.
Oh, okay.
Right.
Oh, that's fair.
Yeah.
Okay.
Oh, angular selectivity. So the way to find that is, you can draw the spectrum, so to speak, the angular plane wave. You can draw the angular plane wave spectrum of, say, the reflection or the transmission as a function of like kx, and then from there you can find out the angular selectivity. So it's like it's typically like a sinc function or a sinc square function. Okay, so where the zero of the sinc square function is. I'm sorry. Yeah, I mean, well, in this particular case, you're doing analog signal processing because you're using the same transfer function to modulate, different spatial frequencies. Uh-huh. Yeah, right. Okay. Well, that's a good question. I mean, I just take it to be the main lobe. I mean, from peak to zero. That's what I usually take. Right. Yeah. Because as you said, from Kogelnick's theory, that formula for diffraction efficiency is like a tangent hyperbolic or secant hyperbolic, something of a kappa times L. And that kappa has those terms with the delta n. Okay, good. Okay, so the thing I wanted to say is here, I think that other video is not working, but typically if the phase shift of the refractive index with respect to the incident light is zero, you do not have what is called beam coupling. Okay, beam coupling means transfer of energy from one beam to the other. That's typically what people have talked about as beam coupling. I don't call it that way because when you talk about a beam, okay, a beam has both amplitude and phase. Okay, but typically in the literature you're going to find, okay, you can only have beam coupling, means energy transfer. You can only have energy transfer if and only if there is a non-zero phase shift, okay, between the intensity pattern falling on the grating or on the crystal and the refractive index change. And that's kind of shown in this cartoon. And this is typically what you see, in such a material. So if you shine kind of like these two beams of light, you're going to find that one of them, is going to extinguish, essentially. The other one is going to be amplified. Now, this kind of thing happens more in, as I said, materials that have this phase shift. The phase shift happens more in materials like not lithium niobate, but barium titanate, for instance, strontium barium nitrate, and so on and so forth. But in materials like lithium niobate, okay, uh, there is this process, certainly. This process is called the diffusion process. But on top of the diffusion, okay, this is just the experimental setup to show that, yeah, you do have extreme beam coupling, as you see, right? But, in these materials like lithium niobate, you have this effect called the photovoltaic effect. Yeah. Say that again. Oh, this setup? Oh, this setup, only thing that's done is light is coming in from the laser from one side and then is being broken up really into two parts, okay, a beam splitter. So beam splitter shows one of the beams going this way, rest of the beam is going there and being reflected by a mirror, right? So a very simple setup. And the power of this beam is actually, kind of much larger than the power of that beam. I mean, here it's hard to say because, the way the picture is taken is by, kind of spraying some aerosol and then taking a picture. So it's kind of hard to say. But this is the so-called pump, if you wish to call it, and this is like the probe. So pump has more energy than the probe. And then what you see here after the wave mixing inside this material, so guess what? The pump has been almost depleted and the probe has gained a lot of power from the pump. Got it? Oh, these angles typically, this was about 30 degrees or so, 35 degrees. So that is actually another good question. I'll come back to that in a second. So angle is important. Because why? The gain of this material, the effective gain coefficient, that means how much energy is transferred from the pump to the probe, depends on this angle. Okay, so it has a peak value at a certain value of the angle. But that is the value of the angle inside the material. So that's another thing you have to be careful about. So the angle in air, okay, is refractive index times the angle inside the material. And typically these materials have refractive index like 2.3, 2.4, and something like that. So 30 degree in air means inside the material is more like 12, 13 degrees. You okay with this? Yeah, so that's the setup. I mean, I don't deal with complicated setups. But okay, I mean, you have to be careful with a lot of details. Yeah, yeah, right, sure, sure. It's the same. Yeah. The other thing I'd like to point out, yeah, no, go ahead with the discussion. Yeah. No, I was going to say the other thing you have to be careful here is the overlap area. So you may have crystal 1 centimeter thick, but overlap area is important. As you're increasing the angle, overlap area is decreasing between the two beams, because that really defines what's called the interaction length, right? So if I have two beams like this, the interaction length is smaller than if the two beams are like this. So there are practical things here. So when people do theory, okay, it's easy to do theory, but when it actually comes to doing experiment and comparing with the theory, you have to think of a lot more other stuff.
Any other material
Oh yeah. This particular one, this one was done using the, of course, as I said, barium titanate, but you can have SBN. SBN is a good material, strontium barium niobate. Then, of course, there is KDP, that's another material, doped properly, KTN, there's a whole bunch of materials. We have actually set up a crystal growth facility in our department where we've started to grow SBN. Yeah. And crystal growth again is another thing. So now this is another thing I would point out to everyone. No one grows crystals these days except Chinese. Okay. So if you want to get started, this is a good thing to do. Grow crystals because electro-optic crystals have a lot of applications. And in this country, there's only one university ever I've seen that has a crystal growth facilities. This Anna University. That's it. Okay. There's a lot of I would say demand for crystal growth. Where crystals otherwise grown? In Eastern European countries, former Soviet republics. Okay, so a lot of crystals, even in this Air Force lab, okay, they have collaboration with former Soviet republics, okay, which are part of NATO now. So you can get the crystals from there. But I mean, again, the main problem we face with this crystal growth thing is people think it's not important. So, when someone thinks it's not important, guess what they do? They send it, and it doesn't make money. That's what they think. So the first thing they do is they outsource it. So where is it outsourced? Guess where? China. Okay. So think about the geopolitics of it. So okay. So now U.S. defense cannot buy crystals from China. Okay. So we have to develop our own crystals or grow in countries like here. Okay, because this is the country that U.S. has good relations with. So this is another thing. Think progressively. Okay, just don't keep doing theory. And crystal growth itself is a big science, and you need to devote your entire life to crystal growth. The only other crystals that are you can buy cheap are these standard lithium niobate crystals, which are still you can buy from China. Their typical cost is like the 1 centimeter cube crystal is like $1,000. That's the price. But more specialized crystals, are more expensive. And where these crystals are very important these days? In LiDAR. In LiDAR, yeah, LiDAR needs beam deflection and quick beam deflection. And okay, in this country, you may think that these self-driven cars are not going to work. Okay, I understand. There are cows, there are goats. Okay, fine. But rest of the world, there are self-driven cars, and they will be there. Even in this country, they will be there, like it or not. Okay, so those cars all go on LiDAR, and LiDAR needs these electro-optic crystals, and they have to operate not in the visible; they have to operate in the infrared. Typically, the wavelength is like 1.5 2 microns. That's the wave. Because you don't want that driverless car to also be shooting out green light everywhere. So they are in the infrared. So this is a great area to get into and establish your footage in the world. Okay, so we are trying to do that, and crystal growth is not an easy science. It's very difficult. Yeah. No, it is there. Semiconductor photorefractives are also there.
Go through the organic industrial part, at the process.
Organic materials are being still made, but organic still has the problem. As I said, you have to apply a large bias voltage. You have to apply a large bias voltage across that photorefractive organic polymer for it to behave as a photorefractive material. Unless that is reduced, that voltage is reduced, which people have tried for many years, but it's still not done. Okay, I mean, these people in Arizona, they are topmost amongst this. I have characterized many of their materials because we had a grant and I used to fly down there all the time. But it's not gone down. Okay, so for commercial applications, if you want to have photorefractive polymers work, they should be biasable at like 10 volts. So anyway, so these are, I hope these are of, of good importance and information-wise to you, what you can do in the future. Okay, so growing crystals you may think is not a great thing. No, it is a great thing to do. All right, I don't want to get into the details of this photovoltaic effect, but all I want to say, everything said and done, because it's complicated, but all I want to say, everything said and done, finally, in these photorefractive materials like lithium niobate, where you have a strong photovoltaic contribution, this space charge field now is proportional to the intensity rather than the gradient of the intensity, which was the case for the diffusion dominated materials. You okay with that? So if this is the case, okay, now this is one of the contributions, not that it does not have diffusion, it has diffusion, but majority contribution comes from this photovoltaic effect. So that being the case, if someone asked me, what crystal would you like to use to amplify light beam? I would not choose lithium niobate because lithium niobate having a large photovoltaic effect, there is not much energy coupling between the two beams. There is a lot of phase coupling between the beams, but there is not much energy coupling between the beams. Are you understanding this? Okay. All right. So how are these materials, so to speak, modeled? Okay. Not easy. Okay. So as I said, I was again very fortunate to be still interacting, as a matter of fact, with the person who, kind of put all these equations together. So his name is Nikolai Kuhterev. So these equations are named after him. And I came to know him about, I would say, like 1992, 93, when, as I said, I had this little crystal of potassium niobate, which I showed you last time, and it developed a hexagonal pattern. So he and I worked on the theory. Little did I know that time, and he's the father of photorefractive. So he, along with three others, wrote this system of equations, actually way back in like 1978. Okay, that's when these Kuhterev equations were first published in, guess where? The Soviet journal, okay, like JETP. And then later on, of course, was translated and so on. So a little bit of history about Kukhtarev. So Kukhtarev is born and brought up in the Donetsk region. Okay, I mean you are hearing about it now, right? So pay attention because these are scientists, well-known scientists. It's good to know where they come from. So he is from the Donetsk region. He got all his degrees, and in Russia he also gets what's called Doctor of Science. Okay, his DSc from University of Kharkiv. Okay, you've heard of Kharkiv? It's always there in the news. I don't know in Indian news because there is a little disparity, I have to admit. But news is there the world over. The city was taken over, certainly by the Russians, but it was partly, part of Ukraine, right? So that's where he got his degrees from. And, it's very sad, of course. Many of his families, of course, had to leave. And in fact, his elder brother was killed recently, I heard. But these are facts of life, okay? You cannot deny that. The other thing is some of his other collaborators, and another collaborator is Odulov, Sergei Odulov, who wrote this original paper on the Kukhtarev equations. He's a faculty at University of Kiev, right? And then he's still there, except the university doesn't open, right? I mean, because they never know when the bombs are going to come in, no matter who says what. I have emails from him, okay? He sometimes hides in the subway, and sometimes he goes to the university. But the university, because Ukraine is in not good condition, right? So they need all the money. You can go to the university and work, but they said you'll not get paid till the situation is stable. So would you like to work there? No. So of course, I mean, people who are really fond of science still work there. Okay, that story aside, so these are the Kukhtarev equations. So here is one equation which is called the continuity equation of charges, really. This is just the regular continuity equation you see in electromagnetics or anywhere. The other one is rate equation, which is how the charges are actually, created. The creation of electrons is also same as the creation of ionized donors, and this is the kind of rate equation for that. So one side over here says that more electrons and hence more ionized donors are produced if you have more intensity of light, as you see, falling on the material. And of course, you lose some because of recombination, because of the traps, which we talked about. Then there is the current equation, which is there in any semiconductor book. The current equation has a diffusion component and a drift component. And the last one is the Gauss's law, which we talked about. So in a sense, you see, this is kind of like Maxwell. Remember, I mean, what Maxwell did? Maxwell's contribution to electromagnetics was he added an extra term, which was the very important term, like the displacement term. Okay, so why these equations are called Kukhtarev equations? Because, well, did these equations not exist before? Well, they're all there, but that group kind of assembled all of these together and then explained the photorefractive effect. Okay, are you okay with this set of equations? That's what's called the Kukhtarev equations. So just moving on, you can actually write down, again, with the Kukhtarev equations, you have to also couple the Maxwell's equations because, light that is falling on the material is changing the refractive index, and therefore, it affects the optical field itself. So you have to solve the Kukhtarev equations together with the Helmholtz equation, which is not an easy thing to do, right? Very difficult. So I know that you're probably running out of time. I'll stop in 2 minutes. I'll continue this and finish it after your lunch break. So what you're going to find is that exact solution, not possible because, it's complicated. So what people do is what is called a perturbative approach. So this perturbative approach was done initially by Kukhtarev, then many others did it. One of the others who did it was Potier. I don't know if you've heard the name. Potier worked with Amnon Yariv for many years. They have books together. And Potier has a book on photorefractive physics. And maybe what I'll do is I'll stop there because what I want to do is just show how the coupling between this Maxwell's equations and the photorefractive equations, can be done very simplified way to show finally what's called the gain equation in the photorefractive, meaning how the space charge field evolves as a function of time, because the space charge field, determines the gain inside the material. So this little part, what I intend to do is just show you just by slides. You don't have to go through all the details, but I'll supply you the notes if you need it. But I just wanted to show by pictures, okay, how the gain coefficient changes, say with the angle. That was a question that was asked. What are typical values of the gain coefficient? How light is transferred from one to the other? And leave it at that. And the other thing I'll say later on is, if you actually write a grating inside this material with two beams, if the material is thin, okay, then you can get non-Bragg orders, right? Like a thin grating, non-Bragg orders. Interesting non-Bragg orders. Remember good old acousto-optics? If you shine, a beam of light, you have non-Bragg orders like Raman diffraction. So Raman diffraction, each of those, diffracted orders, they are related by Bessel functions, first of all, their intensity, their amplitudes. And furthermore, they're all different phases. Because, if you look at the actual solution, it's like the I, or square root of -1 times Jm, okay? And it's square root of -1 to the power of m times Jm. That's the solution. So, that gives me an idea. So all these different lights coming out from these kind of thin gratings, guess what? They are phase shifted. If they're phase shifted, you can use that for phase shifted digital holography. Because in phase shifting digital holography, you need to change the phase of some of the beams. And here you automatically are doing it without a piezoelectric. Okay, so we'll talk about that later. I think Professor Nischel is going to talk about phase shifting digital holography later on. After that, I'll show you how you can use this.
Thing is basically
Right, by 90 degrees each time. Sure. Right? Okay, let's stop there for now because you have to catch the bus. Thank you so much. So I hope you're finding this course interesting here.
Yes, sir.
It's a little bit non-standard because I do not want to follow. I mean, other things you can read up in a book. Well, that's not the way to do it. You have to think differently. All right, thank you.
So we meet at 2 o'clock.
Yeah, I think wherever, 2:15 something, 2:20, 2:30. I think what does it say actually?
It's 107, right?
Yeah, 2:30. Good enough. Thank you.
So when we record a volume holographic grating, if the one beam is at normal incident and the second beam is at 45 degree in air, this for means recording film fills the angle that is approximately 28 degrees in medium. If they have 1.5 refractive index, when we reconstruct.
But this is not a volume grating. Are you doing a volume grating?
Yes, sir.
So why do you say it's a volume grating?
Because the print means the thickness of the grating is sorry, approximately 15 micron.
Okay, but the grating lines are like this.
Yes, yeah.
Okay.
Yes.
All right. All right.
So when we reconstruct at normal incident, we get. But if we have to calculate the angular selectivity, if we incident around 5 degree in air, means recording film fill the angle 5 degree or approximately 2 degree. That is after
Inside,
applying
right.
the Snell's law.
Right.
Okay, but we get the experimental results. Means we didn't.
But this one, as you are reading it out, this is still, I would call it it's a volume grating, but it's still a transmission grating.
Yes.
Okay, yes,
It's
sir.
not a
Yes.
reflection.
Yes.
Yes.
Sir, that's the question that means the angular selectivity is calculated in air. Or in
You have to calculate in air. Well, you calculate inside the medium, but then you have to come outside the air.
okay.
Because all the theory is inside the material.
Means that is not a surface phenomena, right?
No, no,
Okay.
no. It's just a bulk phenomenon.
Okay. But my results are coming out like this. I feel that the recording to record, when we record the recording means
Sure.
in grating, we feel that this is a volume effect, but when we reconstruct it, we feel a surface effect.
So if we use Coulomb transmission grating, if you plot diffraction efficiency versus angle of reconstruction,
Right.
then we get this type of.
Right, which is a
Okay.
sync
Showing
function.
this by the peak diffraction.
Right.
This is FW.
Right, sure. Right.
So along this side, we have angle of reconstruction.
Right.
And this is diffraction.
I agree. Sure.
So if we take this angle from this point to this point, this is the angular selectivity.
That's what I
Theta
would call,
was-
I mean, some people can even call this to be the angular
Yes,
selectivity.
sir.
But I mean, I take that to be the angular.
But actually, I have not found, sir, a reference in previous literature. How to define?
There are
Because
many papers
yeah.
that give,
Yes.
this is the full, this is
Right.
the angular selectivity.
A group of Suzanne W.
Uh-huh.
These.
Okay, that's fine, because the refraction efficiency has gone down by,
Yes,
more than half.
yes.
I mean, that's up to you. I mean, I mean, I just define it like that. Any light coming out.
So, sir, in our research paper. could we-
No, then take it, if you have to refer to someone else, then you can always blame the other person. You can say, according to them, this is the, definition of the angular selectivity. That's what I would do. Because then I have someone else to refer to, meaning blame. Okay, that's their definition. So we are following their definition. Which is fine, yeah. Okay. Thank you. Oh, no, you missed the bus. No, the bus will stop. I'm gonna go and, it's like that old joke, right? I should go and stop the needle from going to 12 o'clock, right? I should stop the bus. Thank you. Oh, the recording. Someone has to stop the recording. Are you gonna stop the recording?